Hi, I'm Bill Mason. This is our electrical course for you getting your license. I'm going to start with how electricity is made. We have a magnet. There's a north and a south end to it. The opposites attract. You can see it moving around. So what happens is we have lines of magnetism, which you could see if you took a piece of paper and took some metal shavings, you'd be able to move it around. You'll see how all the lines of flux show up with the metal shavings on top of a piece of paper. Those lines, they call them flux. That's they're trying to equal out on the north and the south. So it's like two hands trying to hold something. When you have a piece of metal come across it, you have the north and the south trying to hold the atom that's in there, the electron. As you move that metal or the magnet, the north and south magnetic lines of flux are holding it in the middle, and it gets drawn back as if it was like a bow and arrow. The arrow and the electron is, a bow, and the electron is the arrow. As it gets to the point where it can't hold it anymore, it releases. As it comes forward, it's kind of like the knicker-knocker things. The ball is held by the electrons until it can't be held anymore. It's released, slams into the electrons, they all bounce together, and then the last electron kicks out, and that's the reaction. It goes back and forth. There's a couple of things that we have in electrical terms for things that we can explain or show as a graphic. The amount of time that these will go back and forth, we can call that capacitance. Capacitance is the level of retention or capacity that a device, a wire, or a capacitor will hold. In this case, it would be the amount of time that they swing back and forth. The other thing that we have that's not very common is inductive reactance. Inductive reactance would be the amount of energy that is expelled off of when those balls hit each other. Like if they were really hard stainless steel balls, you'd hit into one and it would really blast away, but if they were soft, they wouldn't bounce as much. So you don't get as much reaction off of that. So that's inductive reaction. In school you learn about Ohm's law, but they don't tell you all the pieces of it. Ohm's law works only on DC circuits, and you'll see on all of our electrical components everything is listed in VA instead of watts. VA is volt amps, and the reason why they don't say watts is because for watts you have to have what the total R is, or the impedance. Impedance is the total opposition of current flow as opposed to just the resistance of the wire. When we have alternating current, because it goes from a north to a south 60 times a second in the wire, you have, in audio terms, we'd say flutter. You have this momentum going back and forth inside the wire, and it creates opposition to the current flows. So to create a proper mathematical equation, you have to know what your inductive capacitance is and your inductive reactance is to come up with Z, which is impedance, and then you can get your W, which is your watts. Otherwise you're stuck with your E for volts, your I for amps, your R for resistance. And if you're in a position where you really have to do all this math, you shouldn't be doing it because it's an engineering thing, but you're going to be asked questions on your test on how things work. So as we move along, to recap, we have our north and south magnetic lines of flux. That's how we count how much amperage is going to be, is related to how fast, how many lines of flux there is by how strong that magnet is, and then how fast we whip through this. Because if you picture that we go really slow, or if we took and slam that ball in there, you're going to get more reaction if you do it quick. The electricity is going to be manufactured from the bouncing off of here. Anytime you have a magnetic line going through a piece of metal, you get an induction into the metal. So to first start off, they had DC generators. In a DC generator, you have a north and a south magnet. You have a loop that goes around, and you have two half circles. And the half circles generally have a carbon brush on each side of it. and as it spins around, this side here would stay on the south side of the whole time until it got around, and then this one would come over, and it would be an air brake. So what would happen is you'd have a waveform that's always going in one direction with a little air gap, which would be that space between the two half circles. On an alternating current, you have the same north and south magnet. You have a loop going through, but you have two full circles that don't touch each other, and this one would alternate each time this side comes over to north. That would become north, and when it goes back over to south, this would become south. Whereas this, because of the half circle, you stayed with the same field being south until it had nothing, and then it would be south again. So we have a symbol for our DC, which would be this with dotted line, straight with a dotted line. Our symbol for AC is a sidewards S. The sideward S is taken from the circle. The circle, if you look at it, and I did it in red and blue for you for north and south, it got very complicated to show anything with a circle. So they said, well, if we take half the circle and put it here, and we take the other half and put it over here, it's easy to draw graphs and show you how things work. So at each increment along the way, and it's not linear because it's not in a straight line, it's in an arc, and there's, if you want to get into this tangent and sine of it, you could figure out the math of it. But in general terms, it's about 1.3 volts per degree of angle. So we get up to 90, and you'd have 120 volts here at the top, dead peak, and then it would decay down to 0. And then we'd start the other direction. Now, since you have a north and a south end of the magnet spinning around, these happen simultaneously. So with this going north, south, 60 times a second, that is our hertz. That timing of going from north to south is your hertz, and that's known as your frequency. How frequently does it go from north to south? 60 times a second. That's your hertz rating. So
does that vary at all at any time?
Europe uses 50 hertz. The math is much harder. Ours is a lot. They standardized things back in the 80s with 120, 208, and if you look at the, which I'm going to show in a second, of how they came up with 208, and the same thing is for 277, 480. So on single phase you have 120, 240. Three phase you have 120, 208, or 277, 480. Now with three phase, the only time you have three phase is when you have all three of the hot legs, which we're going to get to in a second here. On single phase, we have two phases that are 180 degrees apart. So you have top dead center and bottom dead center. So this creates 120 volt at the peak. This creates 120 volt at the peak. It's happened simultaneously. So the voltage that you add between A and B phase is going to be 240, because it's 120 and 120 for 240. That's at 90 degrees and 270. That would be drawn out here. For three phase, you have three legs, and they're 120 degrees apart. Now, because of the timing, you cannot have, if you only have a north and a south spinning around, you can't ever get dead center across two things because they're 120 degrees apart. When you're dead center on one at 120, it's in no man's land. So if you drew a line across the graph, you would see that the peak voltage that you get would be at 104 volts on any two legs, hence 208. So you have 120 volt to neutral. Neutral is phase 0. When you look at your transformers, you're going to see it as XO or HO, and H is the high side, X is the low side. So on a three phase, you would have 120 volts at a peak here, and you would be less than 104 volts on the other two phases. But as you come across the timing at